Welcome back, Mustangs, to another edition of No Hair, No Problem. Today we're going to be working on the notes for Unit 1, Objective 4, which has to do with scientific notation. Before we do that, though, I had a real quick question for you. Do you happen to know why was the equal sign so humble? Well, because it knew that it wasn't a less than or greater than anyone else. There you go. All right, so without further ado, let's go ahead and get started with doing scientific notation and standard form. So first off, before we do that, let's talk about why do we have scientific notation. Scientific notation is used because when we really consider what's in our universe, we have very large numbers and we have very small numbers that we have to generally deal with. Large numbers, we're talking about stuff like the grains of sand, the amount of water molecules, the amount of energy. You look at the universe and we're talking about the number of stars and distance between stars. And when we talk about the microscopic level, we're talking about getting down to like the inside of a molecule and then inside of an atom. And in order to do those measurements, we're not talking about like an inch, we're talking about a little tiny bit of an inch. And so the numbers can get either really big or really small, and that's what scientific notation is because we're talking about things that are in the scientific world. And so with scientific notation, when we see like the first one here where we're talking about 6.023 times 10 to the 23rd power, what this 23 means is that we have 23 spots to the right of our decimal place. 23 spots that are all the way to the right. So what would that look like? It would be like 6, 0, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and it just goes on forever, right? Do you really want to write all of those numbers? No. And especially since there's a whole bunch of zeros in there, what's the point of writing all of them if I could just write it a little bit shorter? So that 23 says that we're going to have 23 spots to the right of our decimal. Versus when we have another, let me go ahead and delete this. Auto switch back to your last use, disable it. Okay. What we're saying is in the second case, let's go ahead and talk about if we have like a negative exponent. A negative exponent says that it's going to actually go to the left. So if a number starts with so if we have a negative exponent, it's going to move left, and if we have a positive exponent, it's going to move right. Okay, think about it as like positives on the number line, they always move to the right, and negatives on the number line, they always move left. So again, positive to the right, negative to the left. And that means that what we're going to see in that number would be 0.000000312. So there's a lot of numbers, or there's a lot of zeros that are in front of that 3 there, but that's a lot to write, especially if we have even more. So that's why we just say 3.12 times 10 to the negative 7. Standard notation is writing out the entire number in its entirety, the long way of doing it. So for practice sakes, let's go ahead and look at these, okay? First thing I want you to notice here is that when we look at this right here, both of these numbers are greater than 1. They are bigger than 1. And because they're bigger than 1, what's going to happen is if I was to write this in scientific notation, we're going to go ahead and have positive exponents. Okay, so there's going to be a positive exponent. So what will this look like? Well, to do scientific notation, you take the first two non-zero numbers that are in this number and you just split it right down the middle. So if I move to my left, move to my right from my left here, the first non-zero numbers would be 3 and 2. So what we're going to do is we're going to write 3.2. You just put a decimal right there. Now, after you made that split, you're going to count to the right of it. So we're going to count to the right of it, and you're going to see that over here to the right of it, there are 3 spots there. There's 1, 2, 3 that are to the right. And so what you're going to say is times 10 to the third. Okay, let's do that one more time. So look for the first non-zero numbers to the from the left, and we're going to have 4 and 5. So we're going to go say 4.5. And then we're going to look to the right of this, and we're going to see that there are 5 numbers that are to the right of this. So we see that there's 1, 2, 3, 4, 5 that are to the right of this. That means we're going to have times 10 to the 5th. Okay? So we end up with positive exponents here. Versus when we look at the other ones here, you're going to see we're starting with numbers that are actually smaller than 1. So when we look at these are numbers that are smaller than 1. So smaller than 1. Okay? When we have numbers that are smaller than 1, we're going to have negative exponents. Okay? So again, you do the same process. What we're going to do is we're going to go ahead and look at the first non-zero numbers coming from the left. So as I come from the left, we work across here, we work across, we work across. The first non-zero numbers would be 1 and 7. So what we do is we just chop it right down the middle of the 1 and the 7 there. And you see the number that we have still there. We have a 1 and then a 0.72. So you just write the number that you see chopped right between there. So it's 1.72. And this time what we're going to do, though, is we're going to take into account how many are to the left. Okay, because it's a negative, it's going to be to the left. And so we're going to look at the distance between where we cut it off and where that decimal is. And you'll see in this case that there's 1, 2, 3, 4, 5 numbers that are to the left of that spot. And because it's to the left, we're going to go ahead and say negative 5. Okay, implying that the decimal would be to the left 5. Okay, let's do that again. So looking at this next one here, I'm going to go ahead and make a little line that we're going to use to chop this off. And we're going to go ahead and trace it out. So I'm going to start here. And as we go from the left, the first non-zero number that we encounter is all the way over here at this 2. Okay. So let's write down the number that we see there. That's a 2.5. And then we're going to say times 10 to the. And we have to count now how many are between the, we're going to box it up with our decimal and count how many we actually see there. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 numbers between where my decimal is and where it's supposed to be. And because it's a negative, it's going to be a negative 10. Okay? And that's it. We're just practicing converting between these. So when we look at number 1, this is greater than 1, so it should be a positive exponent. Okay, so let's, again, same as always, let's go ahead and draw our line. Go ahead and separate or move it. So let's box it off. Boom, there we go. Between my first non-zero numbers there, write out the number that we see there. So that's an 8.42. And now the decimal is technically right here. That's where it is. Since I don't see a decimal, it's technically to the right side of it. And now let's go ahead and box out how many spots there are between where I put it and where the decimal actually is. And when we count, there's going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's 8 to the right of it. Okay, let's do this again. Look at this one. This number that we're starting with is less than 1, so we're going to have a negative exponent. Okay, and let's go ahead and start with our line. We're going to go ahead and cut it off between my first non-zero number. So my first non-zero number is going to be that 5 right there. Boom. Cut it off right there. The number that we see is 5.72. Box it out. Look at how many decimal spots there are. 10 to the. There are 1, 2, 3, 4, 5, 6. And so because it's to the left, it's going to be negative 6. Okay. All right, next, let's go ahead and convert to scientific notation. So, I'm sorry, from scientific to standard. So when we look at this, because it's a negative exponent means we'll have a number less than 1. Okay? So what this means is that because it's going to be less than 1, we're going to move decimal left. Okay? Left is going to make it less than 1. So let's start with our number here. 4.31. And we're going to have to move this 7 spots. Move 7 left. All right, now, when I look, let's look closely at this. When I look at this 4.31, I'm supposed to move it to the left. I don't see anything over here to the left of it that I can move it into. So what we're going to do is we're going to throw some numbers over here. Just throw out a whole bunch. Doesn't matter how many, just throw out a whole bunch. And let's go ahead and do the conversion here. We're going to take that decimal that we see right there, and what we're going to do is we're going to move it 7 to the left. You ready? We're going to go 1, 2, 3, 4, 5, 6, 7. Okay? So this is where it was, and this is where it is. Okay? Where it was previously, now where it is. So I wrote some extra zeros in here. I don't need these. This would be my answer here. And again, if we look, there are a total of, between here, there are 7 spots. Okay, between where it was and where it is. And remember that this should be a number smaller than 1 because it's a -7. Okay, to the left. All right, let's do this one more time. Let's talk about what it's told us here. So this 5, because it's a positive, we're going to move right this time. So we're going to move in the positive direction. Again, positive, negative. Okay? So we're going to take that positive and we're going to move it to the right. And we're going to move right 5 spots. Okay? So let's go ahead and write my number. We're going to have 2.47. And let's just create some spots here that it can move into. It's going to be moving to the right. So now let's go ahead and highlight this one and let's get ready to move it. Ready? 1, 2, 3, 4, 5. Okay, so I made some extra zeros here, and let's take a look at this. This is where it was, and this is where it is. And if we look at what happened here, we moved it from where it was to where it is. We moved it 5 spots to the right. Okay, so my actual number here is, just to remember how to do commas if we ever need to use them, 24700. We do every 3 starting from the right. So 3 from the right, comma, 3 from the right, comma, and continue on. All right. So let's look at some big numbers here. 7.9 billion. So there's currently, for our world population, there's about 7.9 billion people. So let's put this into scientific notation. That means let's use a decimal. This is a number that's bigger than 1. And because it's bigger than 1, we're going to have a positive exponent. Okay? This is going to be positive. So let's go ahead and draw in our spot because we're cutting it off. So the first spot is going to be 7. So this will be 7.9. Okay? My decimal technically at the moment is right here after all of those zeros. So let's look at how many spots we would have to move it here and count. There are 1, 2, 3, 4, 5, 6, 7, 8, 9. So I would have to move this 9 to the right. 9. Okay. Let's go ahead and put this in standard notation for the next one. Look at all the signs are given to us. This is 8. So this is going to move right. Because it's a positive, it's going to move right. So it's a positive, let's move it right. So we have 3.33. And to move it to the right, I'm going to have to throw some zeros in here. Just going to throw a bunch in. All right, let's get ready to move it to the right. 8 spots. Ready? We've got 1, 2, 3, 4, 5, 6, 7, 8. Gets cut off there now. So again, this is where it was. This is where it is. Okay. And we look at how many spots took place here. It moved a total of 8 to the right. Okay. So we've got some extra zeros here. I really don't need these. We can cut those off. And if I was to go ahead and write out this number the long way with the commas, we have 3, 3, 3, 1, 2, 3, 0, 0, 0. So we have 3, 333 million. Okay. All right, these next ones. You'll notice right here it actually says to use the calculator. So what we're going to be doing is we're going to be switching over to Desmos. If you have a different calculator, make sure you know how to use it. But this is just straight throwing it in the calculator, okay? For number 6 here, oops. I'm going to have to get these answers here because I did not put it on this calculator. For some reason, I put it on my laptop. And so let's go ahead and see if I can switch over to that somehow. No, we'll just do it on here. It's fine. No big deal. Okay, it's good to know. Good to practice. All right, so when we look at Desmos here, the first problem we had was 4.9 times 10 to the 17th power. So 4.9 times 10 raised to the 17th power. Okay. And then we're going to go to the right. And we're going to cut this off here. We're going to have 3.3 times 10 to the negative 5. 3.3 times 10 raised to the negative 5. Okay. And you'll see we get 1.616 times 10 to the 13th power. So we get 1.617, was it? Times 10 to the 13th power. I wrote that all wrong right there. 1.617 times 10 to the 13th power. All right, just straight throwing into the calculator, all right? Next one, 4.3 times 10 to the 5th. So we have 4.3 times, whoops. So to create that fraction, let's hit the division button that's right there first. So that'll create that fraction right there. And we're saying 4.3 times 10 to the 5th power. 10 to the 5th power. And then close the parentheses. And then we're going to go ahead and do 3.1 times 10 to the 4th. 3.1 times 10 raised to the 4th. And then on the last one, we're going to have 4.7 times 10 to the negative 8. Times 10 raised to the negative 8. Okay. And so when we look at this one, this has it as 28.3617, blah, 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 blah. I didn't put the negative in there. So I'm missing the negative. And that you see that negative just completely changed my answer. Let's put this to just 3 decimal places. So it's going to be 2.836 times 10 to the 17th power. So 2.836. 2.836 times 10 to the 17th power. All right. 2 more problems here. If you were to drive your car at 110 feet per second for 14,400 seconds, that really means that you're driving for 4 hours. It says find the distance in feet that you have driven. So the formula when we're talking about distance, rate, and time is distance is equal to rate times time. When you look at what's given to us in this problem, we're talking about driving at 110 feet per second. That's our rate. And then we're going to drive this for 14,400 seconds. Okay, so that's the rate and time just being thrown in there. So when we take the seconds, we can cross those off. We're left with just feet for our units there. So we're doing 110 times 14,400. So 110 times 14,400 is going to equal 1,584,000 feet. Okay, so if that's the standard form, if we wanted to go ahead and switch this to scientific, remember we just cut it off after our first non-zero number, so that would mean that we're going to have 1.584, and then we're going to have times 10 to the, now 1,584,000 is bigger than 0, I'm sorry, bigger than 1, so we're going to have a positive exponent, and if we look at the distance that it would have to cover to get all the way across this, we would have to go 6 spots there to the right. So that's going to be to the 6th. And then feet, obviously. Okay, 6 to the right of where it currently is and where it would be. All right, the last question here. The speed of light is 11,160,000 miles per minute. That literally means that for every minute, one photon of light has traveled 11,160,000 miles. So then the next part is the distance from the sun to the earth is 9.3 times 10 to the 7th miles. Find the time it takes in minutes for light to travel from the sun to the earth in scientific notation. So let's put in our information that we have. We have d is equal to r times t. The distance that's covered is 9.3 times 10 to the 7th. The rate for this is 11,160,000. And it's asking for time. It actually says, like, find the time. It actually says it in the directions, find the time. So we're solving for t. That means in order to get t by itself here, we're going to divide by that 11,160,000. Okay. Throw this into your calculators, and we're going to get that t is equal to 8.33 minutes. Okay. Just throw that straight into your calculator, let it do the work for you, and you're going to get 8.33 minutes. Now, this is actual data that's being used for this problem. What that tells you is when you have like the sun in space, the sun is going to emit a photon of light. It's going to go boom, leave the sun. It's going to travel to Earth. That light literally takes 8 minutes to go from the sun to the Earth. 8 minutes. That's how far the Earth is from the sun. Traveling 11 million miles per minute. So it takes 8 minutes. So let's sink in. What that means is that when you are watching the sun rise in the sky in the morning, you're not seeing the sun right now. You're seeing the sun 8 minutes ago. Every time you look at the sun, you're looking at the light from the sun 8 minutes ago. When you're seeing the sun set and the sun is actually gone, the sun was actually gone 8 minutes ago. There's a delay because of light traveling from the sun to the earth. Kind of crazy when you wrap your mind around that. And that's why space is so large, because we're just talking about the distance between us and the sun. Now imagine between us and distant galaxies. We're talking billions of years away from us, and at the speed of light, billions of years away from us. Those are very large numbers we're talking about, okay? I personally find scientific notation fascinating. It's very applicable to what we're dealing with in the real world. I hope so far the day one notes make sense to you. If you have any questions, please reach out. Otherwise, you take care and be safe, and don't forget to like and subscribe to my channel. Take care.